So first, I will recap that when we do the activities, we generate energy through metabolic reaction. So that's M. And when we do the physical activities, then we use it as work. Okay. Apart from these two, we also lose some of the energy from heat output, which is QL and QS later on. Okay, and the part that I missed last time is that when when the generation and heat loss and utilization of energy is not balanced, the energy is stored. Okay, and this is the S element. Yep. So in this balance equation, M represent the metabolism energy generation. The unit is watt, and in the balance we use watt per area, watt per surface area of the skin. Okay, the value, average value of the surface area of skins of human body is about 1.77 square meter. Okay, again, the W here, so if you minus your whatever you generate to the whatever you use mechanically, so whatever you use mechanically here is basically energy consumption due to work. Okay, the unit is watt, but in the, again, in the energy balance equation, we use watt per surface area of the skin. So in the equation, the unit is watt per square meter. Okay, what energy that we lose? Okay, we lose it through latent heat loss. We denote it as QL here. Sorry, see, I made a mistake here. It's supposed to be this one's supposed to be plus. So then equal. Equal to the heat loss due to evaporation here, latent heat loss, then sensible heat loss, and the balance. Okay. This is the overall balance, and then we'll do one by one how to estimate it. Okay, the metabolism rate is very hard to know. It will be differ from one person to another. So we use some of the average value. The range is in between 46 to 174. Okay, and then the unit, the common unit is MET. MET stands for metabolism rate. 1 MET equal to 58 watt per meter square. So 58 watt per meter square is like when you relax, do nothing, you don't think very hard. So that is one MET. Yeah. Okay. To give you an illustration, MET give a better unit because it's easy to remember. So you do relax on a sofa, sitting on a sofa, don't think, just enjoying yourself. That is reference 1 MET. When we sleep, it's about 0.8 MET. Okay. When we do light activity, you walk, you're sitting on the park. Okay. Try enjoying the weather. That's about 1.2 MET. Then if you walk, it's about 2 MET. And then if you do heavy exercise, that will be about 3 MET. Okay, that is a guideline. Okay, and then it's also differ from one to another. Women tend to have less metabolism than men. So women is about 85% of men. And yeah, if you have children, it's also less because they are smaller. Okay, it's quite similar to what I explained last week. So this is the reference. The table, you don't worry, you don't need to memorize. You don't need to remember. This is the table reference of the metabolic rate. Okay, it's more or less. Okay, so next, we know, so metabolic rate, we just estimate from this table. We have to adjust, okay, adjust on what activities, and if there is a specification, if it's a man, it's an old person or young person, you need to adjust. It's not really fixed, but it should fall close to the value here, depending on the activities. Okay, so next, you do work. you do work, the easiest way to do it is from, it's very hard to do. It's very hard to do. So we use some kind of percentage. This is also like you need to do your educated guesses. Okay, the highest we can utilize for mechanical work is about 20%, which is when we do heavy physical activities like you sprint, you play badminton, I think badminton, but you really play seriously like an athlete, and it's really zero when we don't do anything. Yeah, so that's reference. So easy. First of all, metabolism, we get it from the table. Work is less than 20% depending on the activities. And next we go for the balance. Okay, we go for the balance. Okay, I explain this one. So the balance is given at the unit of watt per square meter. If you want to know the actual watt, the joule per second, then you need to multiply it by the total surface area of human skin, which is about 1.77 square meter. So let's go one by one to the latent and wet heat. Okay, latent and wet KL can your heat can lose through three different parts. Diffusion of heat with water through the skin, evaporation of the sweat, and then through respiration. Okay, I'll go one by one. So the diffusion of heat is a default equation, which is this one. So where this equation comes from, you don't need to ask. It is really empirical. So people do some measurement and then they try to fit the data into some equation, and they find out these values. If you notice, this equation is different than the one I give you from the previous slide. So it's a function of Ts, which is the skin temperature. So skin temperature is different than our temperature. So it's basically the surface of skin temperature. So it is estimated through this equation. It's 35.7 minus some constant. M is the metabolism rate, and W is work. So that is surface skin temperature. And QD is also function of PS. What is PS? It's a water vapor pressure. Okay, the unit here is in, so whatever you get here is supposed to be in kilopascal. Okay, so PS given from the empiric equation as well. So now I have TS here, I have PS, I'll be able to estimate the heat loss through the water diffusion. Okay, that's number one. Number two, you sweat and then your sweat evaporate. The energy lost through the water evaporation is given by this empirical equation. This is an empiric, so you don't ask where it comes from. It's function of the mass and the weight, the metabolism and the work done. Okay, and finally, respiration is because of, I explained last week, different in temperature of your body and the temperature of the air. So when you breathe, okay, you, for example, inhale 25 degrees Celsius and exhale, because of your body temperature is close to 36.6 probably. So the air will be heated in your lung, and then when you exhale, the temperature of the air increase to about 34. Okay, so the energy that is lost during the respiration is given by this equation. It is a function of TA, which is the ambient temperature. M is the metabolism rate, and PS is here, water vapor pressure. Okay, so next, this is completely different than last week. So when we estimate the sensible heat loss, we use only these two, okay, convection and radiation. And then when we calculate the convection, it will be affected by the cloth that you use. You can use a full body covered cloth, woman with scarf, with hijab. you will have more insulation, so it will affect the convection rate and radiation rate. Okay, and then when we evaluate this heat loss, we use the clothing insulation use a specific unit, which is the CLO. CLO stands for clothing. 1 CLO correspond to about 0.155 meter square degree Celsius per watt. That is the unit. And then the equation related to clothing insulation is incorporated when we try to find out the heat loss through convection and radiation. Okay, next you go. So convection and radiation. Okay, sorry for messy slides. Yeah, I have to upload it last minute because I spent quite some time to find out the correct equation. So it is a combination of two, QC, which is the convection heat loss, and radiation heat loss, QR. So QC plus QR given by this empirical equation. Yeah, this is an empirical equation. Don't ask me how we get it. Actually, there are many other equations, but this is the equation that that belong to the ISO, International Standard Organization or something. So it's a function of TS, which is the surface of skin temperature. TO here refer to operative temperature. Okay, we will discuss later on. ICL is actually a clothing indicator. It will be explained later on what is the equation. It's in the next slide. And then FCL here is clothing factor, which will also be explained later on. And then H is basically the total heat transfer coefficient. We'll explain later on. So first of all, what is the operative temperature TO? TO is given by here, the average of TR times HR. HR is radiation heat convection. The value HR is 6 given here. TR, it's called mean radiant temperature. Okay, it is very hard. So what is this? So basically, for example, what is the mean radiant temperature in my room currently? So imagine if we have perfect black surface. Okay, black surface. Remember, black surface will absorb energy, okay, from everywhere, so that the temperature of that black surface, okay, as if you put it for some time, okay, it will absorb energy and the temperature will go up. So imagine this is the ambient temperature. Okay, this is ambient temperature, and then you have, okay, this is ambient temperature, and you have is it possible to have? And then you have a black here. Okay, black body. So it will absorb heat from surroundings, from anywhere. It will absorb heat, and the temperature will rise. Okay. So it will be slightly higher than ambient temperature. I use a lot of time to find out. So we use this data. Somebody in LinkedIn provide this chart so that I can tell you that the value of TR, mean radiant temperature, is equal to temperature of ambience plus a constant A, in which A is in between here. A is 0 to 1.8. I put it here. 0 to 1.8. This is based on this data. Okay, so then we'll be able to calculate the TO here. Okay, HC is convection heat transfer coefficient. TA is temperature of ambient. So with that one, so HC, it's really depend. Okay, we have two conditions. Okay, first, free convection is when we do nothing. For example, when you sit idle in the room, there is no wind blowing at you. Okay, that's called as free convection. So it is a function of temperature of your clothes minus temperature of ambience here. And this is an empirical equation that given the temperature of the cloth. Okay, what will be the temperature of your cloth? Okay, when on the surface of your cloth. Okay, that's the thing. When under forced convection, so basically when the wind blow at you, so at certain air velocity, okay, at certain air velocity, or when you walk, or when you run, when you play game, so we move relative to the wind, basically at velocity at speed of VA. Then we have this equation to estimate the convection. So we get it all. TO we get, H we find, the S skin temperature we have it from before, from previously. TO we get it here. So now how to get the clothing indicator and clothing factor? So the clothing factor is related to the clothing indicator. Okay, that's one. So this is how empirical equation to estimate the clothing indicator, and then finally the clothing factor is given by this equation. So you need to be able to calculate the clothing indicator, we need a CLO, clothing indicator is the value is here given in this table. And then when we calculate ICL, clothing indicator, we'll be able to calculate clothing factor. So from previous slide, we know how to get TS, TO, and H. Okay, and here you see how we get ICL and FCL. Okay, that's basically it. So I make summary here. So we get an empirical data from a table to estimate what is the rate of metabolism. Then we use this estimation to get what will be the energy for doing the mechanical work. Okay, it's from 0 to about 20% of the metabolism. And then we have energy loss due to the latent. Okay, it comprises of 3. Okay, QL, 2 QL, QS, and we have also the storage S. Okay, you have the storage, and then you calculate one by one. You be given the summary here. Okay, up to this point, there is a slight difference in the equation with the one previous. Okay, any question? Okay, okay, so now I will show you some of the tutorial question. I have only 2 examples for this chapter. First of all, estimate the metabolism. Basically here is M. Okay, work W, latent QS, and sensible heat losses, which is QS, when seated quietly. So we have this equation. This is at the steady state. When not a steady state, we have here element of S. Okay, S is basically the storage. Okay, so metabolism rate when you relax. When we relax, we check from the table, and then we find out that when we relax, it's about 1 MET, which is 58 watt per square meter. That is the metabolism rate. And the next, we try to find out the physical work, W. W equal to mu times M. So the mu value is somewhere between 0 and 0.0 and 20%. Here I pick moderate value 0.05. So it's 5%. So then we can estimate the energy required for work. It's nothing basically. So it's when you do nothing, 2.9 watt per meter square. So we've done metabolism check, work check. Next we do the latent heat. So latent heat we have 3 parts. Okay, QD, QE, QRS. We go with the QE, the easiest one. Okay, this is a function of M and W. We use this one and we get negative 1.3 watt per meter square. Why you get negative in this case is basically we don't get energy. So I don't know somehow how we get this negative value, but it is might be because of there is no evaporation. Okay, you don't sweat. Some water might be condensed at your body, more or less. Okay, so next is you get energy loss due to the diffusion, which is the first fraction. Okay, we look back into the equation given in the previous slide. Okay, we get this equation. In this equation, all are constant except Ts and Ps. So we need to find Ts. Ts is the temperature of the skin. You're given by this equation. And we find out the temperature of the skin is about 34.2 degrees Celsius. Next, we want to calculate the PS. Okay, PS is a function of TA, which is ambient temperature, and this one is relative humidity. So we don't know what is the ambient temperature, so it's really up to you. So mixed weights make sense. It's not ambient temperature won't be minus 10. It won't be 45 or 60. Okay, it has to be somewhere makes sense. Okay, can be 20, can be 25, probably 30 if you're outside. Okay, 27 here I put just in case, yeah. And then humidity is really depend on where. Brunei, I think it's from 60 to around 80 percentage relative humidity. So you key in all of the number, we get a PS of 1.76 kilopascal in this case. And then we substitute all of the parameters into this QD equation to get 3.62 watt per square meter. That is the energy loss due to the water diffusion. And then finally, we calculate the energy loss due to the respiration. So in this term, what we need is M, metabolism, we have it. TA, temperature of ambient, we assume before. And then PS, we estimated before here. So we get the Q loss due to the respiration is 4.69 watt per meter square. Okay, done. Okay, latent heat done. Next, finally, is the sensible heat loss. So sensible heat loss is denoted by QS. It is a sum of the convection and radiation, and given with this empirical equation. Yeah, this is an empirical equation. So TS, yes, we know it. Okay, the rest in this equation we don't know. So we'll start with, I think H. H is equal to this unit. So it's a overall heat transfer coefficient is equal to heat transfer coefficient of convection and heat transfer coefficient of radiation. We know heat transfer coefficient of radiation is constant at 6 watt per square meter Kelvin. Then we need to find out HC, which is the convective heat transfer coefficient. This is the equation for HC. Okay, for HC, we know the temperature ambient. We need to find out the clothing temperature given by this equation. So finally, we get the overall heat transfer coefficient 9.898. Okay, this one is done. Next, we go for TO. TO is equal to TR. Okay, this is the TO. Here, what we don't know is TR. So TR is ambient plus a constant. So I'm here assuming you are inside a room at temperature not so high. So I just give the additional TR, the additional temperature is very low, which is 0.5. So we find out the operating temperature is 27.3 degrees Celsius. Okay, so we get TO done. So next is the clothing indicator and clothing factor. So clothing indicator given by empirical equation. So when we do this one, okay, you need to assume CLO, clothing factor. So clothing factor, I'll go back. It's really depend. Okay, it's really depend and a lot. Okay, where is it? There will be really okay. That's it. So if you are so this is it. So I take this value. So most of the time, I think you will use this value, light summer clothing, because we are in, for example, we are in tropical, so more or less 0.5. If you are using the winter cloth, so this is a light winter assemble. So it's 1.0 is basically closing almost everything except the face. So a woman in wearing hijab will closely resemble this one. Okay, so 1. Men probably 0.75, 0.5, and then when we just use short is this one. So it's somewhere in between 0.25 when you use the short and shirt only, that's 0.25. So it's really from, I will say from 0.25 to 1, yeah, more or less. Unless it specifies heavy winter suit or medium winter suit. So what is heavy winter suit? We basically use 4 clothing, yeah. So thermal, and then you have a normal one, you have sweater, and you have the jacket. So that's 4. So that's heavy winter. So we are in tropical will probably be in range of this one. Okay, 0.25 to 0.25 to 1. Okay, so there where we get the clothing 0.25. Okay, so by using this, then we'll be able to calculate the clothing indicator. So this guy done. So finally, we need to find the FCL. FCL is given. It's an empirical equation. And finally, we'll be able to use this equation here. And we get the heat loss, the sensible heat loss of 17.65 watt per meter square. If you check the balance, okay, you check the balance. Why? QS plus QRES plus Q what? Okay, if you add, okay, so you generate this balance, okay, 58 watt. Then you use 28 for work. We lost 3.62 due to diffusion. We lost this guy due to the due to this respiration, and we lost this amount of energy due to the convection and radiation. We still have left 30.4. So what happened here is that, yeah, one thing is that this energy is being stored in the body. You're forming fat, you're bulking up, or the estimate metabolism rate was too high. Probably it's not 58. Okay, or the work rate is probably not. It's probably too low. It's yeah, more or less. You will always have this. So I've tried many times. Okay, and then I never got it fully balanced. Never got fully balanced because first of all, the equation is just an estimation. Okay, all of this equation. The second thing is really depend on person. Depend on the person. Depend on your assumption on the working condition. Okay, that is solve example 1. Got to solve example 2. In example 2, it's the same as the first one. Okay, sorry. So except that actually salah saya ini. Playing This one is when I think playing squash. I don't know how to spell it. Okay, sorry if I spell it wrong. So what is the difference here? Okay, if you look here, the difference first, the metabolism rate is different. This is a heavy duty sport. So we use different value to start with. Okay, that's number one. Number two is that the physical work also we change. I use the highest here, 0.02. So it's 20% of the metabolism energy used for work, used for sport. The other thing, so the heat loss due to the evaporation is the same because this is a function of M and W. So it's nothing so special about here. But you see here a lot. So basically when you do this kind of sports, you sweat a lot. That's why your QE is high. Okay. The next, you go for energy loss due to diffusion. It's also, something unique here, TS. Okay, TS is skin temperature. You notice the skin temperature is low, 31.8. Okay, why? Because of a lot of energy heat is released to the environment because of the evaporation of E here. That's why the temperature is a bit low. You feel the hot because of your sweat, but when your sweat evaporate, your temperature will go down. Okay, then we get the rest are the same except this something unique here. So you get this energy for diffusion, and then the energy loss due to the respiration is more or less it's just you plug in the equation. So nothing unique of that. Okay, so next for energy loss due to the convection and conduction. So what change is this? Okay, heat convection we use force convection, and then in this case we need to assume what is the speed. Okay, try to Google what is the average speed of things. Okay, of playing squash, I Google myself. It's about 5 meters per second. Okay, that is the only thing different. Another thing different is that I don't know if this is correct. So I here use quite high constant A for the radiant temperature. Okay, I thought of running outside. Okay, but if you put less than this one, if you say that it must be indoor. Yeah, I just noticed it must be indoor. So the energy, no, I was thinking about the question for your assignment. So the question for assignment is running in the Baracas beach. when I do this one, so can be less than this one, 0.5 probably. It's inside, so we'll be able to calculate the TO, the same as the one before. Temperature of clothing, yes, clothing I would say depend, yeah. So it's between 0.25 to 1. Depend. A woman will probably with hijab will cover still all of the body. If you use the jogging suit, you will cover all of the body. Maybe you'll put 1. It's really up to the assumption, but to mention, it cannot be 2, for example, or it cannot be 0. You will not play squash naked. Okay, it has to be make sense between 0.25 and 1. And you key in the equation and you find out this is the energy loss due to the convection and radiation. You still have a positive value. It might be the same as the one before. The metabolism rate was too high. That is one thing. Or the work was too low. Or some of the energy still stored in the activities.